All right, line A4, learning task 4, and it is for B. We're going to move on into the next set of examples that they had, starting over at example number 4. Example number 4 differs from example number 1 in that example number 4 is going to go and give us a capacitor to go and work with. So let's go through our examples. Once again, probably going to be a little bit different than what is shown inside of the book, but that's all right. We're going to go through and just make all these calculations, and finally, after we get through the RCs, we're going to get into those full RLCs and resonant circuits. This one, we're going to go a little faster than the last one because it's basically going to be almost the exact same sort of thing that we're going to be doing out of it. So let's start by identifying what we do know. First of all, we know that we have got power already given to us. It's 3,000 watts that we have over here. We know that there is going to be, that power is going to be set across my resistor, right? The capacitor itself should not go and throw out any sort of power off of it unless the capacitor was starting to fail. That's the only time that we feel heat off of those things. We do also see our volts and we see our amps. And from that, we can go and establish our VA. So we're going to start by establishing a VA. Once we've got the VA, then we can go and figure out what we have got for our VARs. And really, once we get our VARs, then everything after that is going to go and work off of the exact same triangles that we can go and have all the rest of the way across on this one. So let's start with that one there. We're going to go and take 250 volts multiplied by 20 amps, because that's what they give us there. And we find out that our VA is going to be 5,000 VA. 5,000 VA that we have over there. With that 5,000 VA, what we can now do is we can establish our amount of VARs. Now, you should recognize this as being a 3, 4, 5 triangle. If you don't recognize this as being a 3, 4, 5 triangle, or you just want to verify it, what you could do is we could find out this side of our triangle, which is missing our VARs, by using Pythagoras. VARs equals square root of my VA squared minus my watts squared. You take the square root of all of that. When you go through and punch in all of those values, you should end up at 4,000 VARs. 4,000 VARs. Perfect. Okay. Now that we've got that all together, we can now establish our triangle, we can establish our angles, and once we got all of our angles, we can then just work backwards off of all of our rest of our triangles for voltage and for impedance and everything else like that. Let's start by taking these values, my VARs and my watts, and let's assign them an angle. Now we know our watts are going to be at angle 0. We know that my VARs are going to be at an angle of 90. So now we can go and punch that in. We can find that all-important phase angle. Once we know that important phase angle, we can then establish power factor and all the rest of these. 3,000. We're inside of polar format there, by the way. 3,000 angle 0 plus 4,000 angle, this one here, let me just go backwards there, angle negative 90, because we are dealing with a capacitive circuit. We're going to change that triangle, draw it upside down so that we maintain in the proper direction over here. Equals a value of 5,000 at an angle of negative 53.13 degrees. So we are going to go and have our phase angle, theta equals 53.13 degrees. I'm going to draw this triangle over just because I did it in the wrong direction over here, so just bear with me for a second. It is capacitive, which means that the triangle is going the opposite way just due to ice, right? The fact that my current, which is along the 0 axis, is going to go and be leading my value of voltage. So draw this one over here, 3,000 watts, and then we're going to go and have 4,000 VARs, and then our 5,000 VA, and we've got that angle of 53.13 degrees that we have off of it. Lovely. That's the way that it should look. Now, we know we've got a bunch of similar looking triangles. We're going to go and have our impedance triangle. Draw that one. as well as we are going to go and have our volts triangle, because we have to do the sum of all voltage drops, which will be equal to my source voltage. So we're going to have two more that are going to be both at these angular degrees. We know for our voltage triangle, we know what our total volts is going to go and be, right? It's at 250 volts. So I can go and put in 250. We're going to do that in a second, and it's going to drop out our values of volts. We'll see across each of these. We're also going to be able to go and figure out our total amount of impedance, because we know that R is equal to my E over I, which for my source value of resistance, vector resistance, is Z. So Z is going to be equal to my E line divided by my I line that I'm going to have over here. Let's go and find those values real quick. 250 divided by 20 tells me that I've got a total impedance of 12.5 ohms. Drop that one on there. Z equals 12.5 ohms over there. 12.5 ohms Z. And now we're just going to punch these in, each at an angle of negative 53.13 degrees. Let's start with our volts there. 250 angle negative 53.13 equals, I say it equals, it automatically stores inside there, and then we just do that conversion to my XY format. That's going to go and tell me, first of all, my X value. My X value is going to be 150, so that's going to be 150 volts. 150 volts. And then I go and find my Y value, which is going to be 199.99, which is 200 volts that I would have. Where do these volts lie? Well, this volts along the x-axis always falls across anything that's truly resistive. So this is going to be volts across resistance. This is going to be by volts across my capacitor that I would see over there. Lovely. Super simple. Let's do this one as well. 12.5. We're going to put it in at the proper angle. 12.5 angle negative 53.13 equals a value of 7.5 along my x and 10 along my y. What are these values that we are looking at? Well, this is going to be my pure ohmic resistance, 7.5. It's along the x. This over here is going to be my ohms XC that I'm going to go and have along here. So when we take a look now at the main problem itself, we were asked for our VA. We did solve for our VA, that 5,000 VA that we had. They asked for our bars. We did that through Pythagoras. They asked for our capacitive reactance, that's XC over here. They've asked for capacitance in microfarads. We haven't done that one yet. They asked for the voltage drop across the capacitor, 200 volts. They asked for the voltage drop across the resistor, 150 volts. They asked for the resistance of the resistor, 7.5 ohms. They asked for the circuit impedance, 12.5 ohms. They asked for the circuit power factor. We haven't done that yet, but we'll go and take the cosine of our angle to do that. And they asked for the phase angle that we have. So the two things that we are missing is going to be my microfarads and my power factor. Let's go start with the power factor, knock that one off the list. Power factor is simply going to be the cosine of our angle. So we will go and take a power factor cosine of negative 53.13, which gets me to a power factor of 60% that I'm going to go and have. It's going to be 60% leading power factor. 60% leading that we have over here. Lovely. Then this one over here, we need to go and find our actual capacitance itself. For us to do that, we have to go and rework the XC formula. XC is equal to 1 over top of 2 pi FC. We know what our frequency is. What we don't know is our C. So what we're going to do is we're going to multiply C up to the top. We're going to multiply XC down to the bottom. So we'll move C up top here, and we will move XC down to the bottom over here. We've got values for frequency. Value for frequency is going to be 60. And we've got values for XC. Our value for XC is going to go and be 10. So we'll just go and punch that all into our calculator. Bracket 2 times pi, where the heck was pi? Oh, 2 pi times 60 times 10, bracket, and then I'm just going to go and re-invert this one, x to the negative 1, And it gives me a value of 0.000, so that's my milli, 265 microfarads that I'm going to go and have. 265 microfarads over here. Lovely. That is our entire circuit now that's been built together for all of our triangles, all of our power factor, all the rest of that over there. You can go through their way of calculating. There's nothing wrong with their way of calculating. They're using perfectly valid calculations the entire way along. You can go through their figure 6 and through their figure 7, which is just going to be them constructing the same triangles that we just constructed over here. We just built everything by, as soon as possible, moving over to our degrees and then taking our totals. Totals. It's so easy. And honestly, in the field, those are usually the only things you have, right? You get your 250 volts, you're going to have that one. You're going to be able to measure your current, and then from that, you develop your impedance. You know, and all of this stuff is then able to be worked backwards the way that we would in the field. All right, that covers it off for our example number 4. Example number 5 inside of there, they say, example 5, I guess, is just using the exact same one, drawing all these vectors. So 4 and 5 are now complete. We're going to roll on into our example number 6.